20 centimeter thick aluminum slab is placed in contact with a 15 centimeter thick stainless steel plate. The interfacial contact area is 1 meter squared, which is very convenient. Due to roughness of 20%, only 20% of the area is in direct contact, in the gap is filled with air. Assuming that out of this 20% area, half of it is occupied by steel, the other half is occupied by aluminum. The physical system is analogous electric circuits shown below. The difference in temperature between the two sides, the temperature is 400 Celsius. Estimate the heat flow rate. Okay, so this is what we have. Okay, we have an aluminum slab placed next to a steel slab. Now, because these guys are rough here on this side here, the contact is not perfect. So it's not all the steel that's touching all the aluminum. What we have in reality is that we have some air pockets there. Yep. So what we have is three things interacting there: aluminum, steel, and air. Now, we could solve this with this method like here, using the electric circuits like we talked about. And when we do that, we're making one big assumption that you guys need to be aware of. The assumption is that air is a solid, right? Because we're treating air as a solid, because we're only considering the conduction right there. And therefore, that's why this method has its flaws. The other thing we can do is to use the gap contact coefficient. And we're going to do that, okay? So what we're going to have is, we're going to have a circuit like this. This guy here will be R1, and that's the resistance due to the aluminium, depending on where you're from, right? This resistance right there, that's our R1. Then we're going to have a resistance due to the gap. That will be our second resistance. And then finally, we're going to have a resistance due to the steel. That will be our third resistance. Okay, so regardless of the method that we choose, we're still going to have to calculate R1 and R5. We can start with those. R1. R1 is the one for the aluminum slab, and that guy is 0.2 meters thick. Its coefficient is 230. And its area is 1 meter squared, right? As per given in the problem. Oh yeah, one detail that I didn't say, but it's given in our problem statement, is that out of this area here, right, this area in contact, right, out of this area here, so we have 100% of the area, right? That's 1 meter squared. So out of this, 80% is filled with air, according to the statement, and 20% is in contact. Of this 20% that's in contact, we know half and half, right? So half is steel and half is aluminum. Okay, so in other words, the air occupies 0.8 meters cubed of that 1 meters cubed. The steel occupies 1.1 meter cubed, and the aluminum occupies 0.1 meters cubed. Squared, not cubed, meter squared. Right, so coming back to this guy here, meters cuts meters, we're going to be left with Kelvin per watts, and that is 0.00087 kelvins per watts. What is our R5? What is the resistance due to the steel? Steel has 0.15 meters in thickness. Its conduction is 150 watts Kelvin meters, and its area is also same as the aluminum one. This turns out to be 0.01. Okay, so we already have R1 and R5. So now we're missing the resistance on the gap, and for that we're going to use the coefficients. Okay, so this coefficient here, HC, this is going to be a, we usually use H for convective coefficients. We're going to see another H showing up, question 4. Okay, and then it's saying that the coefficient for the gap will be 1 over the size of the gap, which is 0.0002 meters, multiplied by, so check out, it's the area in contact over the total area. So this would be 0.2 divided by 1, right? Or 20%, if you will. And then notice this is meter squared, they both go away. So that's why it's 20%. Right? Multiply by 2K of the two things in contact. So that's 230 for the aluminum and 15 for the steel. Divided by the sum of them. So 230 plus 15. Please get your calculators because we're going to have to do this together. Oh, this is all summed up with, now the area of the void over the total area. So the area of the void is 0.8 meters squared and the total area is 1. So again, it's like 80%, right? Times the coefficient of the fluid, which in this case is air, and the coefficient is 0.032. Didn't put the units down. We can do the units later. Okay, so let's solve this math together. I'm going to grab my calculator and we check the answers. I'm going to hit pause on the video. Okay, so this is a convective coefficient. Okay, this equation turns out to be that. And notice that the convection coefficient, as opposed to K, which is the conductive coefficient, is meters squared, because it doesn't really depend on the distance anymore. And I'm going to talk about that more in the question number 4. For now, all you need to know is that if we want to find the resistance, remember that if we wanted to find the resistance for conduction, we have to do XKA. If we want to find the resistance for convection, we do 1 over HA. So the X is not there anymore. And we'll talk about, I'll explain that better in the question number 4, okay? So if you want to know what is the resistance, we just need to do this. So it will be 1 over 28291.26 times 1 meter squared. Meter squared goes away, we're left with Kelvin over watts. Yeah, please back me up so that I don't do any mistakes. This is the resistance that I got.
You're good, that's what I got.
Brilliant. Okay, so now we just found the 3 resistances. Check it out. We have resistance number 1, where is it? Over here. And resistance number 1, this guy here. Number 5, which is the third one on the list, this guy here. And the one in the middle, this one just is this guy here. Okay, before we move on, I just want you to check the magnitude. Check out the difference in magnitude. See how the resistance from the steel is definitely the greatest. It's actually 2 orders of magnitude greater than the one from the aluminum, which in turn is 1 order of magnitude greater than the one from the gap. That's why I said the gap one is tiny. Okay, so now we can find what is the sum of ours. It would be summing 1, 5, and the one from the gap. Let's put a gap here. Yep. Okay, that's guys agree with me on the number? Cool. So this is what I got. Back me up. See if you guys agree.
Will it be kilowatts per meter squared or just kilowatts?
It depends, right? Did we have an area? Oops, what did I just do? Just did something silly. It's not what I want to do. Full screen. We have an area, we do, right?
Yeah.
So that is the total amount of energy that's going to go through this wall. Okay, but having that said, it wouldn't be incorrect to say per meter squared because this is for 1 meter squared, right? So if we were to double that, we would double the amount of Q as well.
Yeah.
Okay, it wouldn't be incorrect to say that, but this will be fine if you want to say it's 36.68 kilowatts per meter squared. That's also 100% okay because it is 1 meter squared area. Okay, now just for a comparison, just for you guys to have a comparison, if you do the other method, you get 36.77. Okay, so if you do the other method, you're going to get this difference. But what does change a lot is this value here. This value here is quite different. But you notice it's so tiny that doesn't really change much when we're calculating our final Q. But if we were to know what's the delta T on the gap there, right? Our only resistance on the gap will be this resistance here. So that will have a major effect. So you guys can play along with this when you get the videos and use the two methods and practice along. Any questions?